Welcome to the third video in the DSP Tools series. This is by far my favorite tool. It is the tool that shows you how a color map, spectrogram, sonogram, whatever you want to call it, is built. The underlying data behind this plot show how it is calculated on this waterfall plot that is based on this time series available on this other display. And as a bonus, I also have a frequency cut at this display. But I'm getting ahead of myself. Let's start simple. Let's start with the time signal. So in the time signal, you see these shaded regions. These regions are the time frames which are used to calculate the spectra that you see here in the waterfall plot. In blue, I have a shaded region. That blue region is the time frame used to calculate this blue spectrum. So when you want to see how the frequencies of a signal are evolving through time, you don't just calculate a spectrum out of the full length of your time trace. Instead, you take these chunks, these time frames, you calculate one spectra here, you wait a little bit, you take another chunk out of your signal, you calculate another spectra, and then you plot this same data in this kind of displays. Here, maybe it is hard to see, but you have some markers that are colored with the same color of the spectra which they are representing. So in red here, I have my last spectrum, and here I have a marker. And this is something that is very confusing to users that see this plot at first, because the only real data that you have is in this exact line where you have your spectra. Anything between this spectra and that other one, it is interpolation. It is a linear interpolation of amplitudes between this spectra and this spectra. You don't have a continuous data set, but in any case, in the plot itself, it makes it easier to visualize how the data is evolving if we interpolate between the spectra, rather than showing a plot that is discontinuous. So the data that you see here, the colors, they are really this same data. Here I'm plotting the amplitude in magnitude, just because I want to have something different to showcase that I can either plot the amplitude in magnitude or in decibels. But basically these amplitudes here that you see in this axis are exactly the same thing as these colors that you see on the graph. The colors are representing the amplitudes, they are just in a different scale in decibels. This could be Pascal for microphone data, this could be meters per second square for vibration data, or whatever other quantity you want to plot. So you see that the shaded region, it goes from 0 to 1 second, more or less, and that is because at the bottom I have set my default frequency resolution to 1 Hz. If I make this frequency resolution finer, so if I decrease this value, you see that my time frames, they become bigger. In the previous few tools, I explained how this frequency resolution is related to the size of the observation window of the time frame that you take from your complete time series. If I make this frequency resolution coarser, if I increase this value, then you see that the time frames, they become smaller and smaller. Now, you may be wondering, why is there such a gap in between the time frames you are taking? Well, this is another thing that you can usually control on this kind of DSP software. You can define the distance between the windows that you take. Ideally, I think most of us would want that this increment is very small. So you see that if I decrease this increment value, the distance between the time frames here in seconds is getting smaller and smaller. And also I am calculating many more time frames. So I have a fixed length, and whenever I have enough space here to fit another time frame, I will fit them automatically. On the color map, you can really view the effect of this increment. So if I make the increment smaller and smaller and smaller, you see that my color map gets more refined. I can reach a point where my increment is smaller than the size of my time frame. And when that happens, I have overlapping time frames. So this is what you see in this parameter, overlap percentage. Maybe it is easier if I increase the size of the frames, decrease my frequency resolution, Now, if I set the increment to 1 second and my frequency resolution to 1 Hz, I have covered my full time trace here. Well, not all the way to the end, because I cannot fit another window here at the end. It doesn't have enough length. But whatever I can fit a time frame, I have fitted and I have calculated the spectrum. As soon as I make the increment smaller, so 0.5 for example, now I have an overlap of 50%. And I am taking the second window at a 0.5 seconds interval. So this is one of the most important parameters that you need to set when you're doing this type of analysis, this type of plot, the increment. There are some rules of thumb of the value that you can set for this overlap. I like to have at least 50%. Depending on the type of data that I am analyzing, I want this value to be much, much higher, all the way to 90 something percent, even higher. It really depends on the situation. But you see that the smaller increment I use, the more refined my color map looks. But the trade-off there is that you are calculating many more spectra, and that has a cost in processing power. And also the size of this data here is very big, so you end up with huge data sets. The other parameter that you can set is your frequency resolution, and if I make it too coarse, you can see the effect that it has on the color map. But the other way around, if I make it too refined, it also doesn't look that good, right? I'm looking mainly at these diagonals here, these orders, and there is a sweet spot in the middle where I have the best frequency resolution for this type of phenomena. So this type of phenomena you will see normally when you are dealing with rotating machinery, where you have a frequency that is changing over time and that is proportional to the speed of rotation of that particular machine. So as the rotation speed of the machine increases, the phenomena related to that rotation is also increasing in frequency. I have added some other phenomena to this time signal. This is a sharp impulse that you can see as this peak in the time domain, because I wanted you to be able to visualize that if you don't have the correct increment set, you will not be able to capture this phenomena on your color map. I see this very often with users that they see some phenomena on their time signal, but they calculate a color map with the wrong increment, with the wrong frequency resolution, and they don't see that phenomena on the color map. I will not be discussing Hanning windowing functions in this particular tool, but you can visualize that if this peak falls close to the boundaries of this time frame, that phenomena will not be very visible in the plot. If I change the increment such that this peak is right in the middle of a particular time frame, then you can see that that phenomena is more pronounced. Ideally, if you have this type of transient phenomena on your time signal, you would want to set your increment as a very small value so that you don't miss it in your calculations. You can see that when I make the increment very small, that phenomena is very visible in my color map. I also have another phenomena, which is a constant frequency. You can see that if I refine my frequency resolution here, this phenomena becomes very visible, whereas if I make my frequency resolution very coarse, that phenomena gets spread, gets mirrored on the color map. Conversely, for transient types of signals, the inverse happens. They really like very coarse frequency resolution. If you make the frequency resolution very refined, you see that you have a lot of smearing in this type of transient phenomena. So there's always a trade-off with the frequency resolution. You can never get a perfect frequency resolution that will capture your orders, that will capture your tonal components, your fixed frequencies, and will also capture this transient. There's always a trade-off. And that's why I like this tool so much, because with this slider, you can really see that, well, more or less here, I have the best frequency resolution for this type of phenomena. And when I say best frequency resolution, well, there is a sweet spot here where you will get the best resolution, the least amount of smearing for this particular phenomena. This is what I will discuss with my next video. the best frequency resolution for sweeping signals, so signals that are changing frequency over time. So stay tuned. I think this is really something novel. At least I didn't find anywhere on the internet, not even in books, not even in papers, an explanation of how to get this best frequency resolution for this type of sweeping signal. So stay tuned. And if I go very high, I'll have the best resolution for this transient type of phenomena, and if I go very low in the frequency resolution, I have the best frequency resolution for this type of phenomena. There is always a trade-off. One thing, as I mentioned on the previous two videos, that people assume is that if you make the sampling rate higher, you get a more refined color map, but this slider here will show you that that's not really the case. If I decrease my sampling rate, all I am doing is that I am decreasing the maximum frequency that I can visualize, that I can uniquely resolve on my spectra. It is not doing anything to the frequencies below Nyquist. So right now I am at about 810 Hertz. So Nyquist would be at around 405 Hertz, which is the bandwidth. Normally the Nyquist frequency is also referred to as your bandwidth. Why bandwidth? Because that's the bandwidth where you can really visualize useful data, up to 405 Hertz in this case. The reason why you don't really see any data at exactly 405 Hertz is because in the background I am applying an anti-aliasing filter, which tapers off at these last few frequency lines. So that's why you have some attenuation here at the last few spectral lines. But the goal here with this sampling rate slider is to just showcase that, well, you can increase your sampling rate all you want. It will not affect the resulting color map in this lower frequency range. Finally, the last thing that I want to show, if I reset the tool layout, is this frequency cut. So here I am taking samples out of my spectra at a fixed frequency at around 170 Hertz. So I am averaging 3 bins, 3 spectral lines, and I am annotating those spectral lines as these samples that you see here. On the graph, it is represented again by this yellow curve. So wherever this yellow curve intercepts my 4 spectra, I will take 3 spectral lines, 3 DFT bins out of this spectra. I will do an RMS sum of those values, and then I will annotate that amplitude in this sample. I will do the same for the second spectra, the third one, and the fourth one. And the reason why I wanted to show this in this too is because a lot of users, when they do this kind of frequency cut or order cut, they get this kind of curves that are not refined at all, and they don't understand which parameters they need to change to get something like this very refined curve that doesn't look like a sawtooth. By comparing the samples here to this graph, you see that the way to get a more refined frequency cut is to get more spectra calculated. And how do you control how many spectra are calculated? Well, by either increasing your overlap or decreasing the increment for your time frames. And finally, I added a RMS sum region here, where I'm taking the values of all of those samples and I'm doing an RMS sum of them, of course. And this is the value of the RMS sum. So if you're interested in the energy of a particular peak, there's only so much that you can do with the increment. Check that if I make the increment smaller and smaller, this RMS value here is really not changing. I am just calculating spectra that are very similar to each other in this region. So when I do the calculation of these samples and do an RMS sum, this value is not changing because I already captured all the data that I needed to represent this. So if you want to have a good RMS value, normally something like 60% overlap will already suffice. But if you want to have very good amplitude accuracy for this particular peak, then you need to really use a very fine increment. The other parameters that I show here, frame size, it is just the inverse of the frequency resolution. So 1/4 is 0.25. This is your frame size. It is controlled by the frequency resolution. The number of spectral lines in this case, it is not the total number of spectral lines that I can calculate. Normally for a measured signal such as this, when we do the calculation of a spectrum, we talk about how many spectral lines we can actually uniquely resolve. So if you remember from the previous two, I mentioned that with a sampling rate of 1600, if I have a frequency resolution of 1 over a 1 second period, I should have 1600 samples. But since I am ignoring all frequencies above Nyquist, I do not get 1600 spectral lines on my spectrum. I actually get 800 only, half of the number of samples I capture. That's why, well, if I make my frequency resolution 2 Hz, now I have a frame size of half a second. So in half a second, I will capture 800 samples. And with 800 samples, I can only have 400 uniquely resolved spectral lines in my spectrum. Anyway, I hope that was not too confusing. You need to know a little bit about the DSP theory before being able to use this tool, but just by having these sliders here, being able to play with it, being able to see the effect of adjusting the frequency resolution, adjusting the increment in your color map, in your frequency cut, in your order cut, I guess this is a very useful interface to understand these parameters a little bit better. Okay, yeah, that was it. Quick and dirty for today, but I hope it was useful. Thank you for watching and see you next time.